Hello everyone, welcome to my class. Today I'm going to cover continuity of a functions. So let me start the class right away. Informally, a function is continuous if you can draw its graph without lifting your pen from the paper. Now let's define continuity of a functions at a point officially. A function f of x is continuous at a point a if and only if limiting value of the functions equals to the functional value of f at that point a. If the limit does not exist, or if it exists but is not equal to the functional value, then we say f is discontinuous at a. Quick checklist to show whether or not f is continuous at a point. We check these three things. First, the function value is defined. Second, the limit of that function as x approaches to that particular point exists. Third, both of these values 1 and 2, that is, a limiting value equals to the functional value. If any function satisfies these three conditions at a point a, then we say the function is continuous at a. F is continuous on an interval if f is continuous at each point in that interval. Likewise, if f is continuous at all points in its domain, then f is simply called continuous function in that domain. Quick example of continuous functions: polynomials, rational functions, nth root functions, algebraic functions, trigonometric functions, exponential functions, and logarithm functions. These are the basic functions which are continuous on their respective domains. Let me scroll down. If f and g functions are continuous at a, then so are their difference, their sums, their product, as well as their quotients, where our denominator is not equal to 0, are continuous. The constant times the continuous function is continuous. The nth power of continuous function is continuous, as well as the composite function of two continuous functions are continuous. There. Example 1. F of x equals to 5 is continuous functions for all x. This function is continuous being a constant function. Similarly, the g function being a polynomial, actually this is a 8th degree polynomial, is continuous for all x. This implies their sum, f plus g, which is h functions, is continuous for all x. Let me talk about in particular point. Let's say at 0, this h function is continuous at 0, that is at origin, because the limiting value equals to the function value at 0. Let me scroll down. Next definitions. We say fx is discontinuous at a if f is not continuous at a. There are three types of discontinuity we discuss in our class. A removable discontinuity. This is a discontinuity at a point where both one-handed limit exist and are equal, but that equal value is not equals to functional value. This jump discontinuity. A function has a jump discontinuity at a point where both one-handed limit exist but are not equal. The third type of discontinuity is infinite discontinuity. This is a discontinuity where the limiting value of the function is infinity, either plus or minus infinity, as x approaches to the point a from either directions, either from plus or from the minus. That means either approaching a from the right side or approaching a from the left side. Here is a quick visualizations. In the first diagram here, we have a removable discontinuity. Here both one-handed limit exist but are not equals to the functional value. In the B, we have jump discontinuity. Here the left hand limit is 3 and right hand limit is 2. And in the 3, we have infinite discontinuity at 2, because at 2 we have a vertical asymptote. I hope it makes sense. Now let me scroll down. Example 2, list points of continuity and discontinuity of the functions in the intervals, given interval I equals to 1, 8, where 1 is excluding, 8 is including. So the function is defined in piecewise here. So the answers, so points of discontinuity are at x equals to 1, we have a hole in the graph. At 2, we have a hole again in the graph. And at 3, we have a jump discontinuity. At 5, we have infinite discontinuity. And at 8, the function is only in left continuity, so this is also a discontinuity. And the point of continuity are at 4, at 6, and at 7. Good. Let's continue. Example 3. The absolute value functions is continuous at 0. Solutions. Since we know the absolute value function of x has 3 pieces here. Absolute value of x equals to x if x is positive, 0 if x is 0 itself, and negative x if x is negative. If you want to visualize this absolute value function of x here, then on the right side we have this piece here. So if x is positive, we have this red piece or red branch of the graph. If x is negative, then this blue branch is and then for the this black dot, that means when x is 0, the function is 0. Okay, so now to check whether or not a function is continuous, we check the above 3 conditions. So let me show you the definitions of continuities. The checklist guidelines are here. The function value is defined if limit exists, and if function value equals to limiting value, then we see a function is continuous. So now let's check these 3 conditions for our absolute value functions at origin. Let me scroll down again. So here, more better. So first, the function value at 0 is 0. Second, the right hand limit of absolute value function as x approaches to 0 from right is 0. Likewise, the left hand limit of absolute value functions approaching x to 0 from left side is 0. So then this implies the limiting value of the functions as x approaches 0 is 0. Since the function value in part A is 0 and the limiting value from part B is 0, implies the function is continuous at 0. Right? So short and sweet. Now let's move on. Now let's take example 4. Again, we have another piecewise defined functions, and the question is this piecewise defined functions f is continuous at x equals to 2? Again, we are checking those 3 guidelines about continuity. First, in the solutions, first let's compute the function value at 2, which turns out to be 4. I'm picking the x equals to 2 at this middle branch of these functions. And next I'm going to compute the limit. So first, the right hand limit of f at x approaches to 2 from right. It turns out to be from the third branch of the functions. The answer is 3. Similarly, the left hand limit of the given function as x approaches to 2 from left side, from this first branch of the functions, turns out to be 3. Since here both one-handed limits are 3, implies the limit of the functions as x approaches to 2 is 3. But from part A, the function value is 4, so function is not continuous at 2 because the value 4 is not equals to 3. In other words, the limiting value obtained in B is not equals to the function value obtained in A. Okay. So the question is, we can add another question here. Can this discontinuity at x equals 2 be removed? So on the graph here, our functions define the piecewise here at 2. This is just a number 4. And after 2, this is this piece. And before 2, this is straight line. Then the question is, can we remove this hole at x equals to 2? The answer is yes. So that means that limiting value patches up this hole, then this function becomes continuous. So the aside question here, how would we remove the discontinuity of f in example 4 if possible? Okay, so the idea is just, let me scroll down, just define the new functions f, assigning the limiting value 3 at x equals to 2, and the rest just copy the same piece given here. When x is less than 2, f is x plus 1. When x is greater than 2, f is 2x minus 1. Then this newly defined function is continuous at x equals to 2. Good. So that means if we have a removable discontinuity, then we can remove that discontinuity just by redefining our functions and assigning the limiting value as a function value. Great. Let me continue. Let me scroll down here. Now, example 5. Determine whether the functions defined here, f equals to x squared minus 4 over x minus 2 is continuous at x equals to 2. That's the first part of the questions. And the second part, classify the discontinuity of f as removable, jump, or infinite discontinuity if the function is not continuous. Okay, solution. Here the function is discontinuous at 2 because the function value of f at 2 is undefined. So that means the function isn't continuous. That answered the first part of the questions. Now for the second part, if it is removable, then let's compute the limit whether or not the limit of that functions as x approaches to exist or not. So next let's compute the limit here. So limit of that functions, of given functions, as x approaches to 2 equals to here. So we cannot plug x equals to 2 directly here because this gives us 0 over 0 form. So let's apply some algebraic trick here. So let's factor the numerator. Then x squared minus 4 becomes x plus 2 and x minus 2. Copy the denominator as it is. Then in the next step, we can cancel the x minus 2, x minus 2. Then we don't have the fraction here. So we just have limit of x plus 2. Then the limit of x plus 2 as x approaches to 2 is 2 plus 2, 4. So limit exists. So that means the given functions fx equals to x squared minus 4 over x minus 2 has a removable discontinuity at x equals to 2. I hope this makes sense. Now let's continue. We conclude this section with a useful theorem about the continuous functions. We call that the intermediate value theorem. So let me state the intermediate value theorem. The intermediate value theorem says a continuous functions cannot skip values. So the statement of intermediate value theorem is, if f is continuous for all x in the closed interval, then for every value L strictly between f of a and f of b, there exists at least one value c in the open interval AB such that f takes that value c and gives us the output L. So we can visualize this one here. So here in the pictures here, the function f is continuous. Let's say the closed interval is AB. Then f of A is this value, f of B is this value, and let's say this number L is in between f and fb. Then obviously we can find a value, at least one value c in between AB, so that f takes that value c and spit out the value L. So it's clear from the pictures. Now let's do example 5. That's an example for intermediate value theorems. Let me scroll a little bit down here. Good. So example 5, so that the equations 2x cubed plus x equals to 2 has a solution in the intervals -1, 1. So now we are trying to find out whether or not this given equation has a solution. We are computing at least one solutions, but we're not finding exactly which one. But let's see whether or not we can apply the intermediate value theorems. If we can apply the intermediate value theorem, then that guarantees that we do have at least one solution in that given interval. Okay, so solutions. Begin the solution. Let's assume functions fx equals to 2x cubed plus x minus 2. I brought the 2 from right side to the left side. Then clearly this function is continuous, being a polynomial. So that means that's the first part of the hypothesis of intermediate value theorem. Our function needs to be continuous. Then second, let's compute the function value at the end point of the intervals. Here f of -1 is -2, -1, -2 equals to -5, which is less than 0, and compute f at the right end point of the intervals, which is 1, which turns out to be 1, which is positive. So that means we have a 0 between negative value and positive values. That is L equals to 0 in our hypothesis here. Then now we can apply the intermediate value theorems. Then the intermediate value theorem guarantees that there exists a value c in the open intervals -1, 1, such that f takes that c and spit out the value L, which is 0 in our case. Great. So this means that c in intervals -1, 1 satisfies the equation 2c cubed plus c minus 2 equals to 0. That is, c is the solutions of the given equations. So that means we found at least one solutions of the given equations 2x cubed plus x equals to 2 in the intervals I. By the way, this intermediate value theorem is an existential theorem. It does not say in particular which solutions, but it guarantees that there exists at least one solutions of the given equations. Great. So we finish this example 5 as well as the sections 2.5. Thank you.